So for this next video, I want to look at section 7.4 and gravitational torque due to an object's weight. And weight exerts a torque on an object. So let's go ahead and jot that in. When we're talking about weight, we mean the force of gravity, right? We mean Fg. So, anyways, so stationary objects can experience a torque due to gravity. Sometimes the torque is balanced out, so we don't notice it. And the torque of gravity can be calculated by assuming that the object's weight acts at a single point. And this point is called the center of gravity. Now you might think, well, is this the same as center of mass? And yeah, for our use of it in this class, it's pretty much the same idea. Obviously, one is mass, one is gravity, but it's the same idea. Symbol here is a circle, kind of divided in fourths. Then you go ahead and color in two of the sides like that. So we use this symbol to designate center of gravity. So if we look at this question down here, which is example 7.12, I think they tell us that we are given a flagpole which is attached to a point. There's a point of attachment right here to a wall, and we want to know what is the torque due to gravity about this point of attachment. So this is going to be our pivot right there. This angle that we're given is 25 degrees. They also tell us that the center of gravity, I guess we don't know if this is symmetrical or not. Usually when we were given a object, if they tell us it's symmetrical, then its center of gravity is at the center of the object, the very center. They just tell us that the center of gravity is 1.6 meters. So I'm going to go ahead and draw that symbol. 1.6 meters from the wall, or from the pivot or the point of attachment. So that's going to be my R. Right, that's R right there. Okay, and then the force of gravity is going to act at the center of gravity, and it's going to point straight down. And we don't know what Fg is, but they do tell us the mass of the flagpole is 3.2 kilograms. So we can start by finding Fg, right? If we wanted, or we could just work with this. So to calculate torque here, we got to think of our two cases and which one's better. I think this is one of those cases where we already see this horizontal line kind of pointing out to us this side right here of this triangle, and this creating a right angle. And we know that this shortest distance between the pivot and the line of action, or the force line, is called the moment arm, and the moment arm is also referred to as R perp. So R perp is going to be set up a right triangle here where it's going to be the adjacent, right? And across from 90 is going to be my hypotenuse. So when we find these perpendicular parts of R or F, we should notice that the original R or F is going to be the hypotenuse, and the perpendicular component is going to be something smaller than that, right? So anyways, we're going to find torque here because torque is equal to R perp times F, or I'm going to write it the other way, F times R perp. And we know R perp is an adjacent, and the adjacent is equal to the hip cosine the angle. So I can go ahead and write that down really quick. And so I can rewrite that as R perp is equal to R times the cosine of 25. And then F we're going to see is Fg. So we'll see that the torque due to gravity is Fg times R cosine of 25. We know that Fg is the force due to gravity is mg. So we can go ahead and fill in those values. R is 1.6 meters. Now we just got to go get our calculator. We got mine right here. Let's see if I can enter all this in here. 3.2 times 9.81 times 1.6, and then times the cosine of 25. Gives us about 45.52 approximately. Units here for torque are Newton meters. And this is going to be heading clockwise, so we're thinking negative for our torque value. All right, and there you have it right there. Okay, let's go ahead and flip the page. So when an object is free to rotate, it will come to rest with its center of gravity directly below the pivot. So the idea here is this, right? If I'm holding this and I hold it off to the side right here for a second and I'm going to let go of it, the force of gravity is going to point straight down right here. But it's also going to cause a torque, right? We know that it's going to torque and rotate this way as I let go. So once again, if I just let it pivot about my fingers, it pivots so that its center of gravity is directly below the pivot. Because we know that when the center of gravity points through the pivot, it's not going to torque, right? So we know that there's going to be no, if I hold this steady here, there's no rotation this way, clockwise, and there's no rotation counterclockwise. But as soon as it's offset, this force gravity causes that point straight down, causes a torque or a rotation this way, and we see that the wrench moves. The same thing is true if I try and hold the wrench with its center of gravity directly above the pivot, which is now at my palm, right? And if this is the case, if I can keep this center of mass directly, or center of gravity directly above the pivot, the wrench will stay in my hand, it will not fall. But as soon as the center of gravity is offset slightly, then force gravity is going to point straight down, and a piece of that force is going to point perpendicular to the wrench and cause a torque, and the wrench torques and turns and falls and accelerates this way. So if I try it again and if I was to say try it like this and move my hand, right, and balance this wrench, I could maybe stop it from falling. Same is true of a pen. It's actually harder with a shorter object. If I had a longer object like a meter stick and I held it in my hand, I could balance it for a while, keeping that center of gravity in line with the with the pivot. So it is possible to balance an object when its center of gravity is directly above the pivot. You just have to make sure you keep it there. Because if it's directly above, then the angle is going to be 180 or 0 with the pivot, and we know that there will be no torque because there's no perpendicular component of that force to cause torque, and torque requires a perpendicular component. So when gravitational force is directly above or below the pivot, there is 0 torque. And if we had to explain why, we would say, well, because there's no perpendicular component of the gravitational force that would cause torque. We'll say of force gravity. This is when force gravity points directly through the pivot. All right. So what we're going to do then is use this idea that that there's no torque, right, due to gravity when it's lined up through the pivot to find an object's center of gravity. So for instance, I have this wrench that's not symmetrical, and if I put my finger in the middle, it might balance, but it didn't. It appears that this side is more massive, right? But if I kept moving my finger, say, towards the side, right, towards the more massive side, maybe I'd find a point where now the other side starts to torque that way, right? So then I move it towards the other side and try and find that center point. I don't know if you can see that, but that's balancing on my finger. So where it's balancing. So when this happens, it's because my finger is directly under the center of gravity. So even though this object doesn't have all of its weight centered in its middle, there is a point, a special point called the center of gravity, where I can put my finger under that and hold that, and it doesn't seesaw. But as soon as or torque, as soon as I move it off there, it torques. Or if I move it the other way, it torques, right? And so we're going to use that to come up with an equation for where this point is, because maybe I know the mass on this side and I know the mass on this side, and I want to know where this point is on this wrench, where its center of gravity is, right? And that's because that'd be a pretty interesting thing to know, right? To be able to find that. Maybe I hang something from here. Maybe this wrench doesn't really have a mass, and I hang a 100-pound weight here and a 10-pound weight here, and I want to know, well, where do I put my finger so it balances, like a 100-pound weight? Maybe I hang like a 2-pound weight and a 5-pound weight, right? And I want to know, it's like a mobile, right? And I want to balance it. Okay, so you get the idea. So what we have here is a dumbbell, right, with 2 weights. So maybe this could be a 45-pound weight and a 5-pound weight, right? And we want to move this fulcrum or this pivot to a point under the bar where it's going to balance. And we know that if this is the heavier side, then the fulcrum is going to be closer to this side and further from the lighter side, right? Because it's heavier. And we saw that with the wrench. I think when I moved my finger, I had to have it closer to this side because it was slightly heavier than that side, right? There was more mass down here in this end of the wrench. So, all right, so coming back to do this, one of the interesting things we're going to have to do to come up with this equation is we're going to work with a lot of variables, but we can't say the end of the bar right now is at position 0. That won't work because we want to be able to have a generic equation for this, because sometimes when we use this, the end of the bar, say, won't be position 0, or this mass won't be at the end of the bar. So it works better to derive this equation, because we don't know, we want an equation for xcg. We're actually going to call 0 out here, and that's kind of the same reason I don't call this point 0, right, and this point negative x1, and this point positive x2. I can't do that either, because if I call this 0, then I'm assuming something already. So what I'm going to do is set up an arbitrary axis system with just 0 just out here, and all of these being positive points, right? Because it doesn't really matter, and all I'm interested in is the distance r1 and the distance r2. But I am, even though m1 is drawn larger than m2, it doesn't even matter right now, really. So I'm just working with two masses. Let's say we don't know that m1 is greater than m2. We're just trying to write a generic equation to use for the center of gravity. So the first thing we're going to do then is, we know that if this is at the pivot, and we know that if this rod right here connecting the masses together is pretty much massless, then it's a thin rod, so then the weight of m1 is going to act here at this end, and the weight of m2 is going to act here at this end. So that's what we'll go ahead and start by saying. So we're gonna have some torque due to m1, because m1 has a force gravity, right? I'd call this Fg1, and m2 has a force gravity out here, which I can call Fg2. And we know that this force is going to torque this in the positive direction, right? So torque 2 is going, or I'm sorry, the negative direction. Torque 2 is going to be negative, and we know that torque 1 is going to go counterclockwise, is going to be positive. So we have these two torques fighting, and we learned in the last chapter that the sum of the torques is equal to torque 1 plus torque 2. And we also learned here that when the pivot is at the center of gravity, that there's no torque, right? That the net torque is 0. So that's what I'm doing right here with my finger, right? Well, I had it this way. But by putting this here, there's no net torque, and it balances. So we can say that this is equal to 0, and then we can go ahead and add torque 1, the positive torque 1, to the negative torque 2. So that's what I'm going to go ahead and do. Torque 1 plus the negative torque 2 is going to equal 0, right? These two torques are going to fight each other. Well, now the question is, what is torque 1? Well, torque 1 is equal to Fg1 times R1 times the sine of 90, because this force gravity is acting at 90 degrees to the distance from the axis of rotation, right? So we're expecting maximum torque here. On the other, and we're going to add this to Fg2 times R2 and times sine 90. And this is going to be negative. I can't lose my negative sign there. That has to be there. And I'm going to set that equal to 0. So Fg1 is really m1 times g. R1 is really, what is R1? Let's go up here and look. Some distance between x1 and xcg. So an xcg is further away from 0 than x1 is from 0. So we could say R1 is equal to xcg minus x1. right? I want to know the distance between those 2 points. So take the further point minus the shorter point. Sine 90 is just 1, right? I don't even need to write that there, but I did. And then we have this negative sign. I'll just keep it inside there, right there. And so we have m2 times g times r2. What is r2? Well, same logic here applies, but we want distance, this distance just to the pivot right here, right? So x2 minus xcg. You got all these parentheses. Okay, that's fine. And then sine 90 is just 1, end parenthesis, equals 0. So now let's go ahead and rewrite this, because this is getting kind of tough to look at. So I'm going to go m1g xcg minus x1 minus m2g xcg minus x... Oh, did I do that wrong? I think I did that wrong. It should be x2 minus xcg. Apologize. Okay. So now we can go ahead and take a look at this mess. We want an equation that solves for xcg. So we got to get xcg alone. But you can see how we used a sum of the torque balance to even get this far, right? And that the torques have to be equal because the center of gravity is at the pivot. So there's really no easy way around this other than to just get the xcg's out of these parentheses and then move them to one side. So let's go ahead and get them out of the parentheses. So we multiply, we have to distribute. This goes here, right? And this goes there, right? We distribute that through. So we can rewrite this as m1 g xcg minus m1 g x1 minus, and we have to distribute this through, right? So this negative is going to distribute through to here, and the negative times the negative will be positive here. So I'm going to have m2 g x2 and then plus m2 g xcg equal to 0. So right away, looking at that mess, you should be able to see that there's something there that we can get rid of, right? And that because each term has this variable in it. Right, we don't need it. We can just divide both sides by g. We could factor out the g first, then divide both sides by g. Either way, it's fine. So I'm going to rewrite. So m1 xcg minus m1 x1 minus m2 x2 plus m2 xcg equals 0. So let's go ahead and get xcg alone. So we'll kick this term and this term over to the other side. All right, so let's go ahead and do that. Okay, so I'm going to keep this here. Keep this here. Send these negatives over to the other side so they become positive. Then I'm going to go ahead and factor out the xcg. I'm solving for that, right? That's the whole point of this whole mess. And it's going to start to look a lot nicer here. And then finally, just divide both sides by this m1 plus m2, right? We got to get xcg alone. Can't pull anything out of the top here because x1 is different than x2, so we can't cancel this off or anything. So our like we can here. And so our final equation is going to be that the center of gravity is equal to m1 times its position plus m2 times its position divided by the total of the masses, m1 plus m2. So this is a nice equation. Whoops, sorry. This is a nice equation because what you can see here is that it would be valid if, say, you had 3 masses, right? You would just have, if you had a third mass, you would have an m3 or plus m3 x3 divided by m1 plus m2 plus m3, right? You could just add another term in there. So you can very easily solve with an additional mass. All right, so there you have it. Hopefully you got all that written down. You can pause it if you need to. And let's go ahead and do an example. All right, so let's look at example 7.13. And they tell us here that we have a 1 meter long dumbbell. And we attach 2 masses. I think the mass at this end is going to be slightly larger, and the mass at this end is going to be slightly smaller. This is going to be 5 kilograms here, and this is going to be 10 kilograms here. All right, and this is a thin rod, so it doesn't have any mass. If the rod had a mass, then that would change this problem. So then they say that the dumbbell or the rod or we can say that that's attached here is 1 meter long. All right, so far so good. Knowing what we know about center of mass, we have 2 massive objects here. One that doesn't have any mass, and we know that the center of gravity should be closer to the 10 kilogram object, right? So if I had to take a guess for where the center of gravity is, I would say it's about right there. If I put my hand under that point and balance this on my hand, this shouldn't torque, right, is the idea. They say find the position of the center of gravity where the dumbbell should be lifted to remain balanced. So we want to do that. So we'll go ahead and grab our formula. Our formula was xcg is equal to, I think it was x1 m1 plus x2 m2 divided by m1 plus m2. I always get some students that want to memorize that, and that's good. But if you can't memorize it, obviously you can just know something about torques and derive it, but either way is fine. Okay, but it's not given to you on the AP test. All right, so what is x1 and x2 though, right? Well, it's the distance. Well, no, it's just position, right? So it's not even distance, right, from the pivot. This is just position. This is a position. So if that's the case, then we can call this position, say, x1, right? Because I assume this is mass 1, yeah, and this is mass 2. That x1 is at position, we can just say it's at position 0. And we can say that this is x2 then is at position 1 meter, right? So that's going to make things really nice by being able to say that. And so anyways, let's go ahead and solve, right? xcg then is equal to x1, which is 0 meters, times m1, which is 10 kilograms, plus x2, which is 1 meter, or at position 1 meter, and m2 has mass 5 kilograms, divided by 10 kilograms plus 5 kilograms. So fairly straightforward. 0 times 10 is going to be 0, so that can cancel away. So we get xcg is equal to 5 kilogram meters, I don't know what the heck that is, divided by 10 plus 5 is 15 kilograms. Should see what I see, right? The kilograms can cancel away. So we're left with 5 over 15 meters, which is just 1/3 of a meter. Or approximately, right? Approximately 1/3 of a meter is 33.3. Well, now it's exactly 33.3 centimeters. God, I'm struggling here. So what I'm saying is 33 centimeters from 0 right here. This distance would be 33. So if you held the barbell at 33 centimeters from the 10 kilogram end, you would be able to balance it. All right, pretty good, pretty straightforward. Let's go ahead and expand the problem. Let's say that it was the very similar problem, right? But let's give the barbell a mass. So I'm saying this time, let's redraw this. Let's say that we had that mass 1 was here. It's still 10 kilograms. Barbell connects the two masses. Here's mass 2. This is 5 kilograms. And what's the mass of the barbell? I don't know. We'll say 2 kilograms. Now this is a symmetrical 1 meter barbell. Right, 1 meter. So if that's the case, the center of mass of just the barbell, right, would be right in the middle. So this is, we'll call it 2 kilograms, and it is at position, we'll call this, this is mass 3, right? And we're saying this is position, that x3 is equal, it's in the middle, 0.5 meters. All right, so now where is the center of mass, right? Aha. So before it was at 33 centimeters from this end, right, or 66 centimeters from this end, it was right here. But by adding this other mass here, we know it's going to pull this way, right? So we expect it to be closer to the middle with this here. Is it going to be at the middle? I don't know. Probably not. My guess is probably somewhere about right here. I mean, what do you think? So let's just do the problem, right? So we'll go ahead and get our formula. XCG is equal to, we said x1 m1 plus x2 m2, and now we have a third mass, x3 m3 divided by m1 plus m2 plus m3. All right, let's go ahead and plug in our values. So once again, we'll call this point 0, this position 0 for x1. So I can write that in. x1 equals 0 meters, x3 equals 0.5 meters, and x2 is equal to 1 meter. Okay, so I can go ahead and solve down here. XCG is equal to x1, which is 0 times m1, which is 10. I don't know what I'm doing here with these parentheses. Plus m2, which is at position 1 meter and has the mass 5 kilograms, plus m3, which is, plus x3 m3, which is, this is at position 0.5 meters, and it is 2 kilograms. And then we're going to add it to the total mass. Total mass is going to be m1, which is 10 kilograms, or divide it by the total mass, which we have to add up the masses. 10 kilograms plus m2, which is 5, plus m3, which is 2. All right, so we can see that this is going to cancel away. This is going to become 5 kilogram meters plus 0.5 times 2 is just 1 kilogram meter divided by 10 plus 5 plus 2 is 17. All right, so we get 6 kilogram meters divided by 17 kilograms. Cancel the kilograms away, and we're left with 6 over 17 meters. Oops, I'll write my meters on top here. And what is 6 divided by 17? Now we predicted it would be greater than 0.33, right? Or that was my prediction at least. 0.35. Wow. It's greater, but not by that much, right? I guess you could say 0.353. But whatever. 0. So I was not way off, but I was half right? I was correct in that the center of mass now is further this way because you added more weight out here, but our center of gravity is further this way, but I was incorrect in how much further out here, right? I predicted like 0.47. Turns out it only brought it out like 2 centimeters. So yeah, but at least we were right about the direction that XCG was going to move. Okay, we'll do one more example. All right, so let's end with stop to think 7.5. We have 4 light rods with masses attached that go by M or 2M. The pivot point for each rod is going to be different. So I'm going to go ahead and make those pivots red so you can see them maybe a little easier. The length of this rod is a little longer. This has length 2R. So this distance right here is 2R. We're going to see that doesn't affect things too much in a second. This length is R, and this is length R as well. All right, so let's go through and calculate the gravitational torques. And whichever one has the greatest magnitude or amount, regardless of positive or negative, that will be our answer, right? Because we want to know the ranking, right? So we want to come up with something like A is greater than B is greater than C is greater than D, something like that. All right, so for the first one, what we can see here is that this is going to exert a torque this way, right? And it's going to be M times G, or 2mg. So this force is going to equal force gravity, which is going to be 2mg. But if we, and it's going to be negative, but if we call mg Fg, then we can see it's going to be negative 2 times the force gravity, right? I don't know if that's any easier. Let's just keep it as negative 2mg, and we'll be good with that. This one here is going to exert less of a force this direction, clockwise or counterclockwise, but positive, is going to be positive m times baby g, right? Angle here is 90 degrees, so if you really want to, well, we can put that in here in a second. So first off, let's get the distance, right? Torque is a distance from the pivot, so we need this distance right here, which you should be able to see is just r, and this distance right here is also r. So what I'm saying is it's going to be mg times r times the sine of 90, which we know is just 1, right? And over here it's going to be negative 2mg times r times the sine of 90, which is also equal to 1. So the net torque then just for A is equal to the sum of the torques. Let me see if I can write this right here. Sum of the torques is equal to mgr plus negative 2 mgr. So we'll see that the sum of the torques on, or torque A, I'll just keep it as sum of the torques on A, we'll say, is equal to negative mgr. All right, that's for A, right? Let's look at B. For B, what we have to notice here is that even though there's a forced gravity due to M, it's directed through the pivot. So remember, forces through the pivot exert zero torque. So why is that? Because R is 0, right? So let me show you what I mean here. Let's just go ahead and say this exerts a force, right? And this exerts a larger force. And you can see it looks similar to last time, right? But when we sum the torques on B, we get for this mass, right, we get mg times 0. Because there's no R, there's no distance from the pivot. M is at the pivot. So times sine 90. Long story short, this whole thing becomes 0, right? And we're going to add it to what? Well, this is 2m, it's distance r from the pivot. So we can say, negative 2m r, 2mgr, and that's sine 90. Okay, so something like that, right? And so sum of torque B is equal to negative 2 mgr. Sine 90 is just 1, so we can leave it like that. So it looks like torque B is winning right now. Let's just, in terms of magnitude, this one's larger. What about C? Looks like the opposite, except now the 2m mass here is going to exert 0 torque because it's at the pivot, and this one's a distance away. So it should be the same as B, except instead of a 2 here, we'll just have an m there, right? So I'm saying that the sum of torque C is equal to negative mgr. And if that doesn't make sense, then I would work through that and convince yourself that that's true. All right, part D. Now we have no masses at the pivot, but we have this mass being a shorter distance away. So this distance here is 1/2 r. So what that's going to look like then is when we sum the torques, both of these are going to exert a forced gravity which is the same, right? But this one's further out, but they're both going to be negative. So the sum of the torques, notice that the sum of the torques is not 0. It's only 0 when when it's in equilibrium, right? And in all three of these cases so far, these objects are not in rotational equilibrium. Okay, so coming back to this, then we can say that the sum of the torques equals, this would be negative mg times 1/2 r, right? Something like that. And then right here, for this one, it would be negative mgr. Oh, sine 90, right? Don't want to forget that, even though it's obvious that that's just 1. And we're going to add that to a negative mgr sine 90, and that's just 1. So what I'm saying here is we have the sum of the torques equals negative 1/2 mgr minus mgr. So this is really one whole, right? So we got negative 1 1/2, or negative 1.5, or negative 3/2, right? I'm going to go with that. And that was for, I gotta be careful here, this was for D. Alright, so magnitudes, right? Which one, I don't know if you can see all these at once, which one is the largest? We got 2 MGR, 3/2 MGR, MGR, MGR. It should be obvious, right? So we have B being greater than C, greater than A equal to C. So I'm saying, let me say that one more time. I think I said that right. D is, B is greater than D, is greater than A equals C, right? And yeah, and that's it. So hopefully there's your final answer. I can write a note there, final. The final answer. All right, so there you go, final answer. All right, that's it. One last thing. In general, the center of gravity lies closer or further away from the heavier mass, and we covered this earlier, but it should be closer. All right.